homework questions or any general questions? You guys okay?
There was a problem on the homework that I needed help with.
Yeah.
If you have time.
Yes. And I am well aware, by the way, real quick, I'm well aware there are several homework problems that are interesting, right? Have you noticed any in the homework that have been like interesting? Okay, they're supposed to be. The whole thing is every now and again you're gonna get pushed a little further than you've been, just so, again, see if you can do it, to see how you feel when you come into adversity, because again, your students are gonna feel the same kind of way. Yeah.
Okay, it was 3.1, section A, number 18.
Oh, okay, all right. This is the one you guys immediately recognize, the one with all the circles and the little things. Remember this? And they had numbers in all of them. Yes. And you were asked to figure out what's so magical about this. What have you tried?
I couldn't find anything.
What did you try though?
I looked at the addition and the multiplication.
Okay, I like it. So, for example, there's a 7, there's a 14. You could put it over the overhead, on the overhead, Jeff, I know. 13, 2, 19. So this is one little piece of it. Right? And then there's more. There's like another triangle here, and there's another triangle here. There's all these triangles. What is 1 plus 14 plus 7? 22. What's 1 plus 19 plus 2? Right? And then you start wondering, let me look everywhere else, right? I sort of gave the whole thing away, but the very first thing I hope for is that a problem, a sequence, or a problem like this is based on addition. Because that's the easiest thing to kind of do quickly and keep track of, right? So that's the first thing you kind of rule out. And if it didn't work, if this wasn't the same as this, maybe every triangle adds up to be the same as the next triangle, right? Then you can kind of step out. So a lot of these problems are all about, do you feel comfortable enough coming up with different things to try? Yes? That's what a lot of this is. And that's what a lot of, when you're a little kid, you haven't been shut down much yet, right? As much. When you get older, you get shut down more and more and more, so you start to feel like, why would I even try something new? That's very bleak, I'm sorry, very cynical. It doesn't have to be that way, but it's okay. But when you're a little kid, you're ready to try whatever the hell. Let me try this, right? Anyway, so what was my point with that? The problems are all about feeling comfortable just trying whatever comes to mind, right? There could be something about these problems that the book or I don't even realize. That you're like, I tried this and it seems to work. And I'm like, holy shit, that's neat. I've done that before where a student has done something and I just worked on it. And I'm like, you're right, it works in this situation, but not this situation. Yeah, anyway. That's enough of that. Anything else from the homework?
I have one. I'm still kind of confused on sharing versus measurement division. I can't really.
Okay, so the example I gave on here is, so sharing is exactly what you would think it would be. And that's when I had so much money and I was going to share with everybody so much money, right? Or the example I gave on the little thing is 40 apples. You have 40 apples and you want to divide them. You want to share them between 10 bags, right? So sharing is when you know how many people or things are going to get the apples. That's sharing. If I had 40 apples and I wanted to give 5 of them to each person, how many people would I be able to give 5 to? That's measurement. Because I don't have a set group of people I'm going to share with. Apparently I don't even care who I'm going to give it to, right? So what's my example here? Yeah, 40 apples. I want to put 10 apples in every bag. how many bags do I need? So I don't have bags that I'm gonna share evenly with. I have apples that I wanna measure how many bags will hold so many apples, right? Does that, it's not I don't agree fully with the word measurement. There's gotta be a better word, because sharing captures exactly what it is. I have so many people, I wanna share, right? Okay, yes?
Oh, 3.2A, and then it was 24B.
Oh, okay, this is the one with the multiplication. The numbers 1 through 9 will not work. Can you make a multiplicative magic square? Right, so the numbers, you're gonna use 9 numbers. Now, all right. It's almost, I can't even imagine, all right, I'm trying to figure out a way to give a hint to this without just telling you. There is something in multiplication that becomes, how do that's even more cryptic. That's like Yoda's, I don't know, that's like, you know, you go to something and, you know, don't tell me a riddle, just tell me how to do this. No, you must come with the, no, you know. Let me tell you this. What's the operation here? What am I asking you to do with these two things? Multiply them. Yes? Isn't the problem multiplication?
Yep.
How will you do it though? We're going to talk about exponents today, but I know you guys know exponents. So how many 7s are here?
2.
How many 7s are here?
5.
So when I multiply them together, how many 7s do I get?
7.
Good, yes? So to multiply things with like bases, what do I actually do with the powers? Add them. Somehow, what I just said tells you what to do here.
Get it?
Right? So, what's 1 plus 4?
Cool.
Holy shit. What is 2 to the first times 2 to the fourth?
2 to the 5th.
2 to the fifth. Right?
Yeah.
All right. That's all I'm going to say.
Okay.
And if you can't quite, again, the answer is not the point on a lot of these kind of problems. It's what you try, and you got to show me some attempts if you can't quite get the answer. Right? Because sometimes you'll have an attempt that didn't work, but it's interesting. And I want to see that shit. Right? Don't hold it back from me. Okay. So, I don't know. Hopefully that sparked, or that will spark something. All right. Thank you. Anything else? Okay. All right. So just remind you guys, I'm Jeff. It has been a while. I think we did talk about the division thing a little bit. Oh, go ahead.
I have a super random question. When you sent the 2 emails that said that like you weren't gonna be here, it said John, and we were very confused.
So my
yeah.
name is John Jeffrey Waller.
Oh, okay.
Yes.
Well, I can't believe this.
I've gone by Jeff my whole
So
life.
funny.
I've gone by Jeff my whole life, right?
Yeah, I was like, I
Yeah.
don't
Yeah, I
know
read
if
that
that's
email,
her
I
name,
was like,
John.
who's John?
I got you. I've gone by Jeff my whole life. The school, the best I've done with the school is I'm listed in the directory as J. Jeff Waller. They will not let go. Anyway, all right. So I always forget that I'm like John in a few places. I log in a web advisor as Jeff.Waller, but where's I can't remember. My email is Jeff.Waller. They gave me that. Yeah. Anyway, so that explains that.
Okay.
So it's not my my brother John. So I'm like, he's my John. Take care of all my shit, will you? Thank you, man. All right. Okay. So let me ask you this: if a student does this kind of thing here, let's review a few things. They have this question, and they think to themselves, what method are they using?
Missing out.
Missing addend, 11, right? And that's a very natural thing to do. And like I told you, you always try to teach them something that ties into something they know from before, right? So what are they doing if you ask them to do this?
Missing factor? Missing factor?
Missing factor, kick ass, right? Because the elements of an addition problem are addends or summands, and the elements of a product are factors. So that's a missing factor approach. It's crazy. I like it. So that came up, the missing factor, which is just like the missing addend. Let's see, what else do I want to say? Can somebody give me a really fundamental definition of multiplication? What does 8 times 5 mean? Was one of the most fundamental definitions we can give for that.
We can
You have
say,
8 different groups of 5 things in each one.
Sure, so how would you get the answer?
You could basically add everything.
There you go. So isn't it repeated addition?
Yeah.
Okay, so multiplication is repeated addition. This would be, technically, common core makes a difference between this and this. This is 8 5s, and this is 5 8s. And of course, they're the same answer, correct? But it does, this is where I disagree with common core a little bit. It sort of does make sense to kind of make a difference on it, but it doesn't really, and that's where parents kind of lose their shit. Oh my God. But you're like, it's fine. So this is based on repeated addition. So does anyone remember when we start talking about division, what would you want division to be somewhat based on?
Subtraction.
Repeated subtraction. So if I wanted to do 24 divided by 8, how would I use repeated subtraction to do that?
You just subtracted 8 until you got to 0.
Yeah, you said 24 minus 8 minus 8 minus 8, 0. Right? Which is neat to see. Does anyone think that's a little neat to see? Because you don't look at it this way. And you're like, I knew the answer was 3, and there it is, freaking 3. But it really, it just makes sense. If multiplication is repeated addition, and division is the opposite of multiplication, then division should be based on repeated subtraction. Now, obviously, if I had 25 divided by 8, will it work perfectly?
No.
But it will still get you the answer. I would just have, I'm not going to change all that. I would just have 1 left down here, right?
Mhm.
Remainder 1. It still is based on repeated subtraction. I like it. Okay, I love you guys. All right. Blah, 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 blah. And then, of course, we had a lot of fun talking about we talked about these properties twice. Closure, commutativity, associativity, and distributivity. Okay. And the very last thing we did was talk about what this means. And what is that? What's the answer to that?
Undefined.
Undefined. I like it. Yes. Okay, so that pretty much catches us up to now. And I did put something on Canvas, and I realized in the middle of my brain fog, I never unlocked the module it was sitting in. So it's a video from last semester. We're basically going to do that lecture today. So don't worry if you didn't watch it. It was my fault for not getting. And I don't think I told everybody this. I budgeted so much time for chapter 4. I have no idea why. Because 4.1 and 4.2 is chapter 4, correct? So we're actually doing fine as far as pacing goes. It's kind of crazy. So past Jeff must have known something. I don't know. Got a little ESP. Okay. So now we're in 3.3. 3.3 is going to be nifty. We'll see if you guys agree with me. We're going to answer a few burning questions. I don't know what that means, burning questions. What's it burning? I don't know. Well, what does it mean for whole numbers. Whole numbers. If I have whole numbers A less than B, can anybody give me some idea of what that means? What does that mean? Like, what the hell do you want from me, Jeff? That's so fundamental. You can think of it, is there a visual way to describe what that means?
We can do 2 less than 5.
Say again?
2 less than 5.
Sure. That's an example. Well, what's it mean?
We need to add something to 2.
Oh, okay, okay,
Sorry,
sure.
I watched the lecture already.
Oh, okay, you're good, you're good. There's nothing wrong. If you watched it, that's fine. I can't be upset about that. You watched it? I can't believe it. So we're gonna talk about that in a minute, because that's the kind of way that people don't immediately think of. What about on a number line? What would it mean? What is it about the number line that tells you that this statement is true?
2 is left of 5. 2 is to the left of
Good,
5.
2 is to the left. Right?
To the left.
Okay. 2 is to the left of 5, so that's what another way to think of this symbol. Right? The symbol points to the number that is to the left of the other number. Be really careful if somebody said it's closer to 0. Because will that work for negative numbers eventually? No. So I want to establish, even though we're only talking about whole numbers, establish what will work more broadly, right? So since 2 is to the left of 5, it's less than 5. It's crazy. Now, let's go back to what you're saying. This technically means that there exists an n so that a plus n equals b. If a is less than b, there must be some number, n, so that a plus n equals b. So in this case, what would n be? 3. Crazy. And this is the way, of course, that doesn't immediately come to mind, correct? But the minute you see it, okay, that makes sense. If the number's less, that means it's lacking something. And if you add what it's lacking, it becomes the other number. It's crazy. So what I want you guys to do is to prove this property I'm about to throw up here. No, I'm fine. It's called the transitive property. I hope I haven't even looked at my, okay. And what it says is, given whole numbers, if A is less than B and B is less than C, then A is less than C. Prove that using this idea.
We could do,
Don't say anything, yeah. Let me give you a little clue. I already wrote for you a statement you can write because of this, correct? There it is. What statement could you write because of this?
B plus n.
Almost, not quite. Does it have to be the same number, right? If this is 2 and 5, n is 3. If this is 5 and 87, n is not 3 anymore, right? So we've seen this before. We've done this exact thing before when we're talking about odd and even numbers. If I didn't want it to be the same odd number, I used n already, I would just use m, right? So what can you write since we know this? So here I know a plus n equals b. Here,
B plus n
b plus m
equals C.
equals c. So now you know these two things, yes?
Yes.
See, this is the part, this is so close to what is the most awesome thing about math. This is so close to it. You just start writing things you know are true and see where they lead. Yeah, and you're all like, whatever, Jeff, man. You can do that in your free time if you want to. But it's the coolest thing. All right, some of you guys are like, oh, great job, Jeff. You freaking gave us more letters. Yay. But this one says B plus M is C. Okay, do we know anything about B? Do we know anything about B?
No, A plus N.
We know B is A plus N, don't we? Can we replace it over there? If I see B anywhere, can't I replace it with A plus N? Okay, try it. I love you guys. I see some of you guys are like, so you got letters with other letters. This is amazing, Jeff. We already do that. They're called words. Leave us alone. But look, I really want you guys. What is N plus M? It's just some number, correct? Let me call it. Give me a letter. Z. I love it. A less than B means A plus N is equal to B, and vice versa, right? B less than C means B plus some number is C. If A plus something is C, then A must be, if A plus something gets me to C, then A has to be smaller than C. So that's the proof. If I know this and I know this, it leads to this. It's either a car or we're being teleported into a mothership. I'm sorry, guys.
Oh, I know.
It's been good. Oh, it's a car. Okay. There he goes. I don't know. Is that trippy or is that not that terrible? Or that's like some of you guys are like, well, I call this property the Dove property because this says if Alfred is younger than Bob and Bob is younger than Charlie, then Alfred is younger than Charlie. And you're all like, wow. Right? So I will sometimes call this the duh property because it is kind of duh. But it's kind of nifty to see how to prove this given these conditions. Okay. And if you wanted to do it, I was waiting to see if anybody thought about doing it visually. If A is less than B, it must be to the left of B. If B is less than C, C must be to the right of B, correct? And from the picture, you can see A is less than C. And visually, here's N, here's M, so here is what we call Z, right? Is that cool? Okay, I'll stop. That's the deepest dive anybody ever did into less than. Yes? All right. Okay. And by the way, some people I've noticed still have trouble telling the difference between those two for whatever reason. I always think about less than as an L that fell over, right? It's an L that kind of like was like, oh God, fell over. Yes? So it looks like an L, less than. It's crazy. Okay. I don't like the alligator with her. Alligator gonna eat you. Hopefully you guys have heard of the alligator thing, right? I was just realizing if none of you had, I was up here mumbling about alligators. You're like, is he really okay? Oh, good. That's exactly what I was going to say. Good. Then we have this guy. Addition property. If A is less than B, then A plus C is less than B plus C. Right. So let's test this out. 2 is less than 7. Holy crap. If I add 3 to both sides, Is 5 less than 10?
Yes.
Yes, okay. And this is that idea, a quick little side note, I don't know, I don't think I said this, okay. Before I do the side note, visually, why did I pick 7? There you go, John. 2, 7, so if I move them both up 3, obviously the one that's bigger is still bigger, because their relative distance from each other is the same. Right? Okay. But here's something interesting. What is, let me see, you can do it, Jeff. Yeah, what's 40 minus 7? Holy shit. Is 41 minus 8, I should have given you this one first, but 41 minus 8, you'd have to think about it for a second. Anybody? It would be a little bit worse than this. Does anybody agree with me?
Yeah.
A little bit, yes? But do you understand how these are the same problem?
Yeah.
Yes?
Yeah.
Because if I take one away from him and one away from him, I've kept the distance between them the same, which is what subtraction wants from me, is how far apart are these things? Maybe? Okay. So that's kind of a neat little thing. I think that might come up in chapter 4. Chapter 4 is all about mental math and estimation and stuff. I know. Okay. Then there's this one is the big one. Okay. Then there's the multiplication property. I'm going to go a little further than the book does with this. Remarkably enough, if the addition property was if you add, it stays the same. And again, this is for whole numbers. Remind me, what does whole number mean, basically, really quick?
Positive numbers.
Positive and 0, right? So if I have whole numbers a and b, and a is less than b, then a times a whole number is less than b times a whole number. So as long as everything involved is a whole number, that is true. Kind of makes sense. If you're making more than me at a job, and our boss doubles our salaries, you're still making more than me, yes? I didn't suddenly leapfrog you somehow, and if I did, then you're like, what the shit? Okay. Now here's where things get interesting. We're going to introduce a little bit more than the book does. I think this is a good place to do it. Let's bring in negative numbers. Does anyone remember what happens when you multiply or divide by negative in an inequality? So, for example, like back in algebra, if you had to do this, solve for x, oh shit, remain calm. I don't want to bring back anybody's algebra OCD or trauma. What happens, how do I solve this for x? Does anyone remember? Divided by the thing that's with x, right?
Yeah.
Divided by -1. Does anyone remember what happens?
Does it switch the sign?
Yeah, the sign flips. Why? Why? Here's your assignment, kids. Tell me why. I don't know. I know why. So let me show you an example of why this is true. Does anyone know why this is true? Does anybody remember this? You guys remember this at all? Not at all. Okay, shoot.
I remember
No, I remember
doing
it.
it, I just don't remember why.
Okay. I actually had 2 ways to show this is why this is true, but I'm going to give you, this is the most straightforward way. Which one of these is bigger?
2.
Holy shit. If I divide both sides by a -1, what does this become? And what does this become?
One.
Which one's bigger?
One.
What happened? What happened? Sign flip, right? So why does the sign flip? Because. I love this answer. Because that's how numbers work, right? So think about this. If something is smaller than something else, if A is less than B, that means A is to the left of B, correct? I really want you guys with me.
Yes.
Let me put 0 here just because. stay with me. I'm throwing a lot at you out of nowhere, but I want to go through fully down this road. When I multiply by a negative number, here's a cool thing you probably never looked at it as. When I multiply something by a negative number, it rotates to the right? So and if I multiply this by a negative number, it's going to go over here. It didn't have to go further. I'm not drawing to scale. Sorry. Which one's bigger now? This one is bigger now, right? So if A is less than B, if I divide both sides by -1, now we're saying this is bigger now. Yes? Because they switch sides. So it's called, this is a, that's right, this is the phrase I forgot to say earlier. This is a non-order preserving operation. Holy shit. This is a non-order preserving operation, because whatever was in front of the line, if you multiply a negative, the whole line switches, yes? And everybody, it's all turned around. Does that make visual sense? Okay. So the earlier thing, if I have A less than B and I add 1, it stays the same, yes? That's an order preserving operation, remarkably enough. Because just adding 1 doesn't change what line, if you're both in line and somebody skips way ahead of us, we're both one step back than we were, but I'm still in front of this guy. It didn't change the order, right? But if suddenly that window closes and that window multiplies by a negative, oh shit! Now you're in front of me. Although I don't think that would ever happen. That would be really okay. Maybe? Is this trippy, or does this make sense, or you're just hoping I stop talking about it and keep going, or okay, all right. You're all like, I'm not going to say anything, and just hope you keep going. Okay. So I brought negatives in. The book doesn't bring negatives in yet, but since we're talking about inequalities, I wanted to bring this up just to really put that to rest. Oh, okay. So any questions so far? I mean, this is, like I said, it's a much deeper dive than you thought probably would be possible about inequalities, right? Okay. And believe me, this is the tip of the iceberg, so we're not going to explore the rest of the iceberg. Now we've got, Now we've got, one of my favorite topics. And as always, so what kills me was when there's one of my colleagues, or just a teacher anywhere, who's just telling students this is how you do it, this is what you do, not why you do it that way. So there are properties of exponents that you have to memorize. So like we did earlier, did we add the exponents when we multiplied, correct? Yes? Why do we do that though, right? That's the more important question. Because then it's less memorization and more just doing what's correct, what's the right thing. So what is the fundamental definition of exponents? Well, let me tell you a little story. I know this, just hang with me. So somewhere in the universe, let's say the Earth, there was somebody who had to write this in a paper he was writing 1 billion times. This is not leading to exponents yet, correct? What would this be? Yeah, that would be 6x, correct? But somebody had to come up with that notation for the first time. It's shorthand, yes? And we've talked about this, and again, this is multiplication being repeated addition, correct? But that's shorthand for this. Is there any 6s in this problem right now? Any 6s? No. So what does that 6 mean? There are 6x's that are doing what to each other? Adding. So coefficients are repeated addition of the same thing. So this other dude, this is the drunk history of this. Although, am I drunk? No. This other dude, at the same time, or like a year later, let's say, he's got this, and he's like, damn it, that guy, God, he took my idea. Damn it. So he wanted to put a 6, and he wanted to mean multiply x 6 times. Because he didn't want to keep writing this dumb thing, right? So he's like, all right, let me maybe I'll put it here. That looks like division. Maybe I'll put it here. That looks weird. Maybe I'll put it like that. No, no, screw that. Right? Sure, why not? Yes? This is important for you guys to know. Maybe it's kind of difficult to shoehorn it into a conversation with elementary school children. But it's really good to stop and think every damn thing we do had to be chosen to be done that way at some time. There's no reason this 6 had to be right there. They just said, 6 here means multiplying it 6 times. And everybody was like, great. And the one guy disagreed. They shot him. It was a different time, right? You guys with me?
Mm-hmm.
This definition is what makes every other property of exponents what they are. So if you don't understand this, you can't understand anything else about exponents. So for example, so this is the fundamental idea of exponents. So what about the properties? So if I add like x squared times x cubed, so the long way to do this, what does x squared mean?
2x.
Yeah, x times x times, and what does x cubed mean?
X times x.
X times x times x. And then you go back to the definition, correct? Not that one, but this one, yeah. So what would this be?
X to the 5th.
X to the 5th. And then we realize a shortcut, because why does multiplication looks like it becomes addition? Let me ask you this. In this problem, is there a 2 or a 3 anywhere in that problem?
Yes.
There is no 2, there is no 3. There isn't. I love saying that. Because then students are like, oh God, this guy's really tripping. What does that symbol mean?
2.
There are 2 x's, right? And this symbol means there are 3 x's. So of course I'm not going to say 2 times 3, because there isn't even a 2 or a 3 in there. To multiply, there isn't. There's 2 x's sitting next to 3 x's, which makes 5. So the shortcut, screw this, shortcut is add those. Of course, because that's how long your list would be, your list of x's. 11. I know this is basic shit, but I just want to make sure you guys have all seen the full explanation. What about division? What happens with division? What happens if I have like x to the 5th divided by x squared? Well, let's try it this way, right? Oh, sorry.
Do you subtract x?
Yes, you do, but why? So up top you got x, 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 x. And since it's division and multiplication, they're going to kill each other. How many x's die?
2.
2. So I do start with 5, and I lose 2. So yeah, screw this bit. I can just do 5 minus 2, right? It makes sense. If multiplying like bases leads to adding powers, dividing should lead to subtracting powers. And again, I know you guys should know this. What about, let me ask you this. Okay, how do I put this for your notes? Question. What is 2 times 3 to the 12th power? Is it 6 to the 12th power? What do you guys think? Is 2 times 3 to the 12th? Is that 6 to the 12th?
No.
How many 3's do you have?
12.
How many 2's do you have?
1.
So how many 6's could you make? 1. Do you kind of see what I'm saying? You only have 1, 2. How could you make 12 6's? Yes? Maybe? Maybe? And of course this is going to lead into order operations. We're going to talk about that in a minute. Get out of here. That's a crap. What is 2 to the 12th times 3 to the 12th? Yeah, now you can do it, yes? You have 12 twos, 12 threes. Multiply those. How many sixes can you make? 12. Do you guys see the difference there? And it really is. It totally just is. Isn't this 1, 2 with a bunch of threes? Yes? Couldn't you only make 1 6 then? Times the rest of the threes? You can't make 12 sixes. Are you crazy? Now you got 12 twos, 12 threes. You can make freaking 12 sixes. Yes?
I had a question, I wanted to say it's 24 for some reason, because I know like over here we added the exponents.
Are the bases like? This is a really good question. I want you to realize what's happening. Here, these are both x's. So what am I doing? If somebody was looked at me and they said, all right, we got 2 chairs and 3 chairs. And they're like, why didn't you just say freaking 5 chairs? So this is an idea of consolidation. Why would you say x squared, x cubed? You just say x to the 5th and get to the, give me a break. Here, I've got all my 2's together. I've got all my 3's together. Right? There's 12 2's and there's 12 3's. So this is like somebody saying there's 12 chairs and there's 12 tables. Right? And if I want one table having 1 chair at it for some reason, then how many table chair things can I make? 12 of them. I don't know, that's a bad analogy, but table chair, Jeff, I don't know. I really want this, these bases are not the same, correct? So I don't suddenly have more of something, right? I can't make 24 sixes if I only have 12 threes and 12 twos. Okay. I like it. So it's got to be like bases for the power to change. Okay. Let's see. What about? Oh, what's the point of that, Jeff? Oh, yeah. Maybe we should finish this idea. So this kind of leads to this idea. A to the m times b to the m equals a times b to the m. Oh man, all right. So I'm about to bore the shit out of you in a minute. Hold on. You guys are like, this guy's boring me. Just wait. I haven't even get started. Math teacher, that's my superpower. Boring people. Now, I want you to understand what I'm about to say. That looks like distribution to me. Does anyone agree? If I start on this side, doesn't it look like I distributed that? Right? What is distribution though? Wouldn't distribution be this? That's what we call distribution normally, yes? Somebody remind me, what is a coefficient based on? Remember the 6x? What was the 6? What was that based on?
Addition.
Addition, repeated addition, yes? 6x is added. I want you guys with me. So this is based on addition. It will play well with addition. So I can distribute the m, no problem. What are exponents based on? Multiplication. So it's going to play well with multiplication. And it's a beautiful analogy here. If I have A times B, and I got M of those, that must mean I have MAs and MBs. I mean, that only hopefully makes sense. All right. Is it warm in here or is it just me? Probably just me. Okay. Need to re-up my minutes. All right. I don't know, how many people did that trip out? This is a property called power distribution, because it just freaking makes sense to call it power distribution. That's what we do. In fact, you guys know this. I know you know this. Somebody help me out. What is 2 cubed? 8. So what is 2x cubed? 8x cubed, right? Didn't you do the 3 to the 2 and the 3 to the x? That's all that thing is saying. That's it. That's all it's saying. Okay, I like it. the last thing about these exponents for now. Let's see if anybody remembers what this is. What would, a to the 0 be? You guys think it's 1? Anybody have a different idea? All right, good, it's 1. Yeah. Okay. A few different ways to see it's 1. My favorite way to see it's 1 is to use an earlier property. What kind of division problem, if I put a squared here, what's got to be down here so the answer is a to the 0? Remembering what we do when we divide. What do we do with the powers when we divide? So this would have to be a squared, right? Because then 2 minus 2 is 0. But what is something divided by itself? Okay, right. Another kind of nifty way is, what's the only number I can multiply by, and the number I multiply by stays the same? We call it the identity, right? The multiplicative identity, that is, no, that makes everything 0. I want to multiply by something that keeps it the same. 1, right? So if I already have 7, if I multiply by 1, still 7. Yes? So watch. What is a to the 0 times a cubed? What do? You add the powers, right? 0 plus 3 is 3. So what must this be then? Since it left it the same, it's got to be 1. There's another proof. Okay, maybe. And one more, just because I'm trying to get you guys to go crazy and to be bored beyond tears. A squared. If I divide by a, I lose an a, I get a to the first, yes? If I divide by a again, I'll get a to the 0, but a divided by a is 1. Okay, and that's basically the same thing we already said. All right, enough of that. So anything to the 0 power is 1, except, here, let me really push it. What the shit would that be? What is 0 to almost any power? 0 squared, 0 cubed. It's 0, right? But what did we just say anything to the 0 power is? 1. So you have answer always 0, answer always 1. I like it. It's even worse than undefined. It's called indeterminate. All right, that's going a little bit beyond our curriculum, but I just thought I'd throw that at you. Okay. Last thing, and then I want to show you some videos, and don't get too excited. This last thing might, well, we'll see. Maybe not the last thing. What am I talking about? Well, we'll see how I'm feeling. Order of operations. Remember, I think I've talked about this a little bit already, but have I told you what's the saying for order operations? PEMDAS, what's the saying?
I don't know.
You could change it, yeah. I'm going to say it, and it makes you sound drunk if you try to change it. PEDMASA, right?
Yeah.
PEDMASA. Please excuse my dumb-ass son. Oh, dear Aunt Sally. Yeah, that's the traditional one. The dumbass son is one I made up. And then my class a while back, they said, please excuse my deficient algebra skills. They made that up for themselves. You know, so I was like, unfortunately for some of you guys, so some people write it like this, which is completely wrong. And I like that you said what you said. It tells me that somebody at least is showing what's wrong with this. These don't, multiplication does not always come before division. Addition does not always, it could have been this. But which one's easier to say? Of course. So we made it the first one. So both of these are shit. All right, so here's the right one. What does this stand for?
Parentheses.
Parentheses first,
Exponent.
exponent second,
Multiplication.
as it comes. They're both same level. Nobody wins. So that is the, all right, this is the way I write pendants, right? Order operations. Some people think division is always last. And that drives me a little crazy. There's no reason for that. So let me give you a problem. Let me see what you guys do. Well, let me do this. Yeah, there you go. It's better. All right. Go ahead and try to do that. And then we'll do it together. Awesome. All right. So what did somebody do first? Yes, good. So do 3 minus 5 first. And that is
Negative 2.
good 2. I like it. Anybody make that 8?
No.
Okay, good. And then of course, what's next?
5 minus 2, and then multiply the parentheses with the exponents, which is positive 4.
Now, I do have somebody, now I don't think you meant this, but I have had people do this. What's wrong with what I've written?
It wasn't added, it's still.
Good. It's positive 4, but this has changed. What is the operation supposed to be?
Multiplication.
Yeah, good. All right. I know this is really boring. So just stay with me. Now,
2 times 4.
yeah, so from the very beginning, I could have asked you, what are you going to do last? What's the very last thing you're going to do? Subtract. Why is division not necessarily the last thing we're going to do? Because it's not at the ass end of PEMDAS. Addition and subtraction is at the ass end, right? So this 5 is 5 minus stuff. So the 5 just sort of like, come on, what are you? This, what's the only operation in this whole chunk? The only operations. Multiplication? Is either one of those more important than the other one? Nope. So you just do it as it comes. Right? The reason, if anybody did make this an 8, just didn't want to say it because the way I asked it, it's not fair to make this 8. Because I'm only dividing by 4. If you make this 8, now I'm dividing by 8. That's not fair. What the hell happened? The only number that would be on the bottom is the 4. Does everybody see that? That's why these can't become 8. So if I rewrote this, it would be 5 minus 2 times 4 divided by 4 times 2. That's another way to look at that. So how the hell do those make 8 when one's on the bottom, one's on the top? Right? So these can't make 8. Yeah. So what do we get here? 2 times 4 is Divided by 4 is 2 times 2 is 4. Yeah. Okay. I like it. So desperately exciting, I know. I have heard, and I have seen now, teachers that actually taught multiplication came before division. And they just make every math person's job that much harder, because then we're all assholes. The minute one of us does that, we're all assholes, right? And I see constantly, anybody still on the old person Facebook? Just the old people? All right. Every now and again I'll see on Facebook, somebody's posted another frickin' order operation. What's the right answer? And everybody's like, 417. I'm like,
Yeah.
what is happening? Anyway, so why this idea is the grammar, right? It's sort of like, in certain languages, don't you put adjective after noun? Instead of saying White House, you say house white. You guys know that? Like, I believe it's Spanish, right? Don't you have house white instead of White House? Okay. So this kind of tells me what's supposed to happen first, what's supposed to happen next. It's the way that we're supposed to read these sentences out correctly. And that's the accepted way to do it. Here. I'll give you one that looks easy on the face of it. What's that? One. 16. So I got somebody saying 1.
16.
Somebody saying 16. You guys find that interesting that there's 2 different answers at the moment? Anybody else think they got the answer? Yes? 16? 16? Everybody else is like, all right. So you gotta be careful because division is not necessarily last. Well, see, the only operations in here are multiplication, division. You do them as they come. 4 times 4.
16.
Divided by 4.
4.
Times 4.
16.
Yeah. Does that make sense? But again, I know exactly why so many people think division is last. It's because of this. Yeah. What's the last thing you would do in this problem? Divide. Right? But if I were to write this problem in a straight line, because does your some of your calculators do nowadays, but I was going to say, does your calculator have a big ass division line? Some of you guys do. But 4 minus 2, if I write it like this, is this good? Does this capture the same idea?
No.
Hell no. So what's unfortunate about this notation is there are hidden things in it. There are understood parentheses that don't need to show up because we understand they're there unless we do this. That would make division last. Why would division be last here? It's the only thing not in parentheses. So of course it's last, right? But in that problem, straight through, right? Okay, maybe. All right, I think I'm feeling better. I was just feeling a little bit wobbly. I'm going to try to do a couple more things. Watch a video that's not going to be a cute little kid, sorry. We'll get the cute little kid fixed next week, right? Or what is today? Yeah, next week. Let me ask you what you think about this. Is there a way to rewrite this? You could rewrite the division symbol, but
You could do A plus B and then put the line and then C.
True. In fact, all right, let's do that. Now, is there anything I could do with that? I like what you're thinking, but it's not an equation, so I don't have another side to kind of balance me out.
You could just do A over C plus
Yes!
B over C.
Which seems weird, yes? I understand why some of you guys might not even have thought to do that, because it feels like you're going backwards then, yes? But now let's take this back up here. Look how do I write this like this? Wouldn't this be A divided by C plus B divided by C? What does that look like? Doesn't it look like distribution? All right. This is a little bit strange. Actually, let me just say this is very strange, right? Because the first time I heard about this idea of right side distribution of division was getting ready for this class, to be really honest. We don't really call it this because we normally don't write it like this. But that's very weird. It looks like distribution. It really isn't, because if I put this in front, it doesn't work. Why doesn't it work if I have C divided by A plus B? Why can't I make it C over A plus C over B?
Because that's not what you're dividing.
Oh, okay, good. Here, I'm dividing by C. Am I not still dividing by C? If I thought this was this, here I'm dividing by A plus B. Am I still dividing by A plus B?
No.
No. Oh, shit. Right. Can't do that. But students definitely do that every now and again. I don't blame you because it's optimism. I'm not saying you, but you know. Okay, there's one little thing. What was the other little thing before we do a video? Oh yeah. Just to give you a little preview of the next chapter. I think I already said this earlier, but chapter 4 is going to be all about mental math. It's going to be so, you guys have been waiting, I know, mental math, I love it. It's about estimation. So different ways to estimate. Right, so some old favorites are going to come back. So for example, I know, it depends on how you feel about it, I guess. I shouldn't say that for you. If I said, what's 4 times 37 times 25? Come on, you guys are better than that. Come on, come on.
37,000?
Close.
37,000.
Yes. Do you have to do it in that order?
No.
No. It's all multiplication. And doesn't multiplication have commutativity? Commutativity? Yes. So can't you do 4 times 25?
Yep.
Right? And that's 100. Times 37, so 3,700. Easy peasy. We did that when I said like 8 plus 4 plus 2 plus 6. You find all the tens, don't you? So the broader idea that this captures is something called compatible. Well, how do you spell compatible? Does that look good? Compatible numbers. 4 and 25 are compatible. They both make a nice number, right? What about if I had, you could do it, Jeff. There it is. All right, this is going to look a little weird at first, but too bad. I'm claiming there's something in there that I can do instead of just long divide, or get your calculator out. What if this was 3,300? Wouldn't that be nice? Isn't that compatible with 3? Do you guys agree with me?
Yeah.
And what's left over? If I take 3,300, what's this plus what? To make 3,510.
210.
210. Is that compatible with 3? Yes. What's 3,300 divided by 3?
1100.
1,100. Plus, so I'm using this idea, right? What's 210 divided by 3?
70.
70, right? 7t, I like it. So then 11.7. So I can't list all the compatible numbers, correct? Because there's an infinite number. It's just whatever happens to be 2 numbers or that will make something nice happen, right? Sometimes they're parts of what you're given. Sometimes you have to find them. Is that the only way I could have broken this down? No. It's just the way I thought to do it. Okay. So let's do this. I think that's plenty. That's plenty. I don't want to push myself too much. I'm going to have to turn you off because YouTube will not